The first session of this course is entitled Conceptual and Scientific Foundations of Sustainability. To establish the conceptual foundations of sustainability, I would like to begin by relating an account that begins back in December of 1968 and centers on the launch of the Apollo 8 mission to the moon. The reason that this voyage is recognized as significant is at least partly due to a very special photograph that was taken, the first image of its kind ever captured. This picture, which came to be known as Earthrise, marked the first time that human beings were able, in effect, to stand outside of their inhabited world and to view the planet from afar in its completeness and wholeness, to see the Earth as a whole system. It was the first time that we could observe in a tangible way the isolation of the planet, our home, in the void of space, and begin to recognize in a viscerally and emotionally powerful way that we are all part of a single global community. Such an idea had been talked about in various contexts throughout much of history, but it was always an abstraction. There was never an easily conveyable image that could impart a clear understanding of one Earth. We can regard December 25th, Christmas Eve, 1968, as a hinge in human history, one comparable to the Copernican revolution, or the revolution in thought inspired by Galileo. In other words, the first viewing of this photograph marked a moment in time when people came to understand their place in the universe in an entirely new way. The next chapter in this story occurred 4 years later, again in December, when the Apollo 17 mission sent back home the image pictured here. It may be surprising to hear today, but this subsequent photograph, named Whole Earth, is the single most widely produced and disseminated image in history. Unlike the prior photograph where the planet was partially obscured by shadow, Whole Earth captured the planet in its full radiance. The landforms and the oceans are more clearly visible. Storms are readily apparent, and the image has a discernible luminousness. It is worth pausing for a few moments to compare the two photographs and to think about how the entire human experience and our understanding of ourselves has been forever altered by the ability to see the Earth pictured from space. No previous generation had the opportunity to view the Earth from such a perspective and to marvel at the message that it conveys. The fortunate circumstances that made it possible for us to have this photograph as part of our cultural and intellectual repertoire brings about a sense of awareness about ourselves and the universe around us that is unique to this historical epoch. The Whole Earth photograph in particular became an iconic image for an entire generation, and it had profound effect on human consciousness. It may be hard from the standpoint of today to fully appreciate the significance of this image because it has become so ubiquitous to the point of becoming trivial. You can, for instance, buy a cup of coffee with the Whole Earth photograph emblazoned on it, or a t-shirt. It is even the title of a popular environmental book authored not incidentally by Stuart Brand, a prominent environmentalist and futurist who has played an important role in the metaphorical treatment to which the photograph has been subjected. So, from the perspective of the history of sustainability as an idea, that the Earth is a whole system and that we as human beings have a responsibility to ensure its endurance, the image of Whole Earth is immensely important. Let us partially set aside the Whole Earth photograph for a moment and consider a related question. What distinguishes planet Earth from the vast multitude of other bodies in the universe? I would argue that it is the planet's ability to support and sustain life. As far as we know, there are no other bodies in the entirety of the universe with this extraordinary capacity. Because of the uniqueness of this attribute, I will suggest, the primary objective of all our pursuits, politics, education, science, technology, should be to sustain life in all its wonder. The tragedy, of course, is that many contemporary activities are geared toward undermining rather than upholding the objective of sustaining life. We can think of this as the paradox of modernity, and it has numerous manifestations, many of which you are no doubt only all too familiar. We diffuse immense volumes of toxic chemicals into human tissues. We knowingly practice ecologically harmful forms of industrial agriculture. We release dangerous pollutants into ecological systems. And we have thus far failed to begin to achieve meaningful reductions of greenhouse gas emissions in full awareness of the harm we know that they are causing. We perpetuate design processes that contribute to societal fragmentation and social isolation, and at various turns we deny millions, indeed billions of people opportunities to live with dignity. Unsustainability is pervasive. It is inherent in the way we design and build our communities. It is common in the field of architecture and the way that we conceive and construct our buildings. Unsustainability is integral to the way we design and build our transportation systems, the way we produce and distribute food. It is endemic in the way that we generate and distribute fuel and other forms of energy. Unsustainability is a fundamental characteristic of the way we organize engineered systems of industrial production and the way that we manufacture consumer goods. There is much that is utterly unsustainable in the way that each of us goes about the process of meeting our everyday needs. It is important to recognize that contemporary concerns about the lack of sustainability across a range of activities do not derive from normative or aesthetic commitments, but they are undergirded by rigorous science. The science of sustainability, or sustainability science, centers on the study of biophysical limits and the extent to which we may be transgressing these boundaries. What are the most serious of these biophysical limits? The first limit that I'm going to discuss should be relatively familiar because it relates to the assimilative capacity of the atmosphere to absorb greenhouse gases, principally carbon dioxide from the burning of fossil fuels. The atmospheric concentration of carbon dioxide began to rise with the advent of industrialization during the late 18th century. But the rate of accumulation really began to pick up after World War II. The pre-industrial baseline of CO2 is 280 parts per million, and the contemporary concentration is now approaching 390 parts per million, an increase of nearly 50%. It continues to rise by approximately 1.5 part per million per year. If we keep to our current course, concentrations are likely to exceed 550 parts per million by the middle of the next century. And this raises the prospect of truly catastrophic climate change, a conclusion that has been carefully vetted by authoritative institutions like the Intergovernmental Panel on Climate Change and numerous scientific panels around the world. Atmospheric scientists have suggested that we adhere to a strict limit of 350 parts per million, a level that means we would need not only to a level that means we would need not only to massively reduce current releases, but actually to start immediately to take carbon out of the atmosphere. So the assimilative capacity of the atmosphere is the first biophysical limit, and it is one that we have already transgressed. For our purposes, we will assign it a red star as it marks a boundary that has been crossed. A second biophysical limit with which we need to be concerned is the loss of biodiversity. Scientific evidence suggests that the prehistoric or pre-human rate of species extinction was on the order of 1 species per 1,000 species every 1,000 years, a relatively low background rate. In the recent past, with humans on the scene, species extirpation has been on the order of 100 times greater, and future projections are at least 10 times higher than that still. Note that the scale on the left side of the graph is a logarithmic scale. We are losing species at a rate that is unprecedented in evolutionary history. Though the limit here is a bit fuzzier than it was for the case of climate change, the scientific claim is that we need to get down to a rate of species extinction that is no more than 10 times the background level, less than 1/10 of what it is today. So this is the second biophysical limit that we are currently violating, and it too gets a red star. We have, largely through the widespread deployment of industrial agriculture, massively disrupted nitrogen and phosphorus cycles. Let me briefly take each of them in turn without getting into the technical details. In the first instance, nitrogen moves from the atmosphere into the soil and is taken up by plants and then released back into the atmosphere. Through the large-scale application of nitrogen-rich fertilizers, we have added tremendous amounts of nitrogen to the system that cannot be biologically absorbed, and as a result, much of it ends up getting washed into rivers, lakes, and other bodies of water, where it creates so-called anoxic zones, regions of varying sizes that are no longer able to support biological productivity because all of the available oxygen has been depleted. Phosphorus, another supplement used in industrial agriculture, is typically mined from rocks, where it has been geologically sequestered. When the phosphorus is applied as fertilizer, it overloads the cycling that naturally takes place between soils and plants. The graph here gives some feel for the magnitude of the increases in nitrogen and phosphorus that have occurred due to the advent and diffusion of industrial agriculture around the world. Since 1960, in the case of nitrogen, there has been an 8-fold increase, and in terms of phosphorus, we have tripled the amount. This map identifies the dozen or so areas around the world, most of them located in proximity to major river deltas in regions of intensive agricultural production, that have become anoxic or biologically dead as a result of oxygen deficiency caused by an overabundance of nitrogen and phosphorus. One anoxic zone that gets a lot of attention is located off the coasts of Louisiana and Texas. Nitrogen and phosphorus-rich runoff from the Midwest is carried down the length of the Mississippi River, where it accumulates in the Gulf of Mexico. Biological productivity in the region has been substantially reduced, and the zone continues to expand each year. On a global scale, 121 million tons of nitrogen are applied each year. Scientists have deemed that a safe level would be 1/3 that amount, approximately 35 million annual tons. Similarly, we currently mine upwards of 20 million tons of phosphorus, and this should be cut by a factor of 8 to 2.5 million tons. A fourth constraint, one that is perhaps more commonly recognized, is the thinning of the stratospheric ozone layer due to the use of industrial chemicals like CFCs. We have made significant progress reversing this situation largely through the implementation of the 1987 Montreal Protocol and its successor agreements. But it remains a matter of serious concern due to legal loopholes and various kinds of illicit commercial activity involving the sale and use of banned CFCs. For the moment, at least, ozone depletion can be placed on a watch list instead of being assigned a star, indicating an issue of critical importance. Fifth, the oceans are becoming more acidic, largely as a result of the overabsorption of carbon dioxide. This is a case where we can begin to see some of the intriguing interlinkages among these various constraints. In this case, between ocean acidification and climate change. As we continue to burn fossil fuels, some of the resultant carbon dioxide is finding its way into the oceans. Carbon dioxide is slightly acidic and thus is contributing to a reduction in oceanic pH levels. One consequence of this process of acidification is that coral reproduction declines, and in fact there is widespread evidence of the whitening or bleaching of coral reefs around the world, an indication that the living coral is dying. These coral reefs are obviously important from the standpoint of tourism, but they are also critical marine habitats that support important fish species and a wealth of marine life. According to sober scientific assessments, we are not at a critical point yet, but we are moving quickly in that direction. We're rapidly depleting supplies of fresh water, especially in areas around the world, with large and rapidly growing populations. Climate change is exacerbating the situation as precipitation patterns are altered. At the same time, global water consumption, in part due to population growth, and in part due to the diffusion of more water-intensive lifestyles, has increased by a factor of 8 in 100 years. This is another biological constraint to which we need to be closely attentive from a sustainability standpoint in coming years. Nearly 12% of the planet's land surface is occupied today by agricultural activities, the green line in this graph. The blue line is just a statistically fit trend line. Though there has been a leveling off in the rate of land conversion in recent years, the increase in meat consumption and continued population growth in large population countries like India and China is a worrying sign because more pasture land is required to raise cattle. This also relates back to the water scarcity problem. Global food prices have been on an upward trend in recent years as a response to the situation, compounded to some degree by the shift toward biofuels production, which takes commodity products out of the food supply and moves them to the energy supply. Scientific assessments suggest that we need to keep the amount of land conversion to agriculture below 15% to avoid reaching a dangerous tipping point. Chemical pollution and contamination comes in a variety of forms, from the degradation of marine and terrestrial ecosystems to the absorption of estrogen-masking chemicals among women and testosterone-lowering chemicals among men. The global chemical industry has experienced pronounced growth over the last 60 years, and as the graph here indicates, is expected to grow by a further factor of 4 over the next 40 years, a rate substantially in excess of population growth. Even in the case of one particular chemical application, pesticide use in agriculture, the rate of growth has been nothing short of spectacular. Despite the development of a robust interest in organic agriculture, there is no evidence of abatement or a reversal on this front. The capacity of the biosphere to assimilate and safely degrade all these chemicals is another issue about which we need to exercise extreme care. A final, somewhat more nuanced issue that is just beginning to come to public attention centers on small-scale particulates associated with combustion processes that contribute to adverse effects on human health, especially asthma because they lodge deeply in lung tissue, and ecosystem functioning. These are tiny particles as small as 2.5 microns in diameter, substantially smaller than a human hair, but nonetheless potentially very problematic. The cost of reducing the emission of these particles is, as you can imagine, inordinately expensive, and we are just beginning to learn about the way they interact with biological processes. This is another issue on which we need to keep a close eye. It is important to bear in mind that it's not just a question of concentrating on one biophysical boundary at the exclusion of all others. As I've already intimated, the planetary system is characterized by complex, synergistic, and interactive processes. The oceans, the atmosphere, the soils, human biology, involving various biogeochemical cycles, and we are only now starting to understand and appreciate these intricate processes. The cover of a book by the British geographer John Adams from a few years ago on risk provides a useful graphic for thinking about the dilemmas that we face. The background graphic, extending out beyond the boundaries of the cover, as indicated by the arrow in the upper right-hand corner, represents the realm of potentially knowable knowledge about Earth system science. What we currently know is represented by the small box in the lower left-hand corner. What we know is vastly smaller than what we need to know. As a global community, we are going to have to figure out how to deal with this situation, because we are never going to know with confidence what we really need to know to make progress with respect to these various problems. At the same time, let me offer something of a cautionary word. The Earth system science of sustainability is our point of departure, but we are not going to dwell in any detail on the science of sustainability in this course, as I have outlined it here. The point of this discussion has been to make clear the scientific scale of the issues. In addition, when working from the social scientifics perspective that we will employ in this course, it is important to be cognizant of the biophysical dimensions of the problems that we face. It should be evident that our problems are pervasive and inadequately acknowledged, especially in the world of elite policymaking. There is little question that human resilience is going to be severely tested as global population grows from 6.7 billion people today to 9 billion people by 2050, just 40 years from now. Keep in mind that 2050 is the same distance forward as 1970 is in a backward direction. We don't have a lot of time on our hands. It is also likely that it will not be possible to maintain the chronic inequities that are emblematic of the contemporary world, at least not without having to resort to draconian means of political suppression and military violence. So the task that we are going to be concerned with in this course is how to ensure the livability, and according to some scientific appraisals, the survivability of the planet. This is the challenge of sustainability. Please review the readings that I have assigned for this introductory session, and I look forward to joining you for the next module that we will take up on the international politics of sustainability.